Hey everyone, and welcome. So today we're going to talk about something that's basically the hidden engine of the entire modern internet, but most of us never even think about it. It's called IPv6. We're going to break down what it is, why it's so incredibly important, and try to solve the big mystery behind its rollout, which has been going on for decades now.
All right, to really get why this matters, you gotta look back a bit. The internet's original address system, IPv4, had a very firm limit. It could only ever handle about 4.3 billion unique addresses. Now, back when the internet was just starting, that number seemed almost infinite. Yeah, turns out that was a massive miscalculation.
Okay, now compare that to its replacement, IPv6. The number of addresses here is 340 undecillion. That's a 340 with 36 zeros after it. I mean, it's a number so huge it's kind of hard to even wrap your head around. You could give a unique IP address to every single atom on the face of the Earth, and you'd still have plenty left over. It is practically unlimited.
And that gets us to the big mystery of this whole thing. If we completely ran out of the old addresses, and this new system gives us, an infinite supply, why is this switch taking decades? What is the holdup? Well, the story starts with a really clever patch, a workaround that essentially put the old system on life support. It delayed the crisis for years and years, and it's a huge part of why the internet works the way it does today. And that clever fix is called Network Address Translation, or just NAT for short. Just think about your Wi-Fi at home, right? You've got your laptop, your phone, maybe a smart TV, a tablet. All of them are on the internet. But your internet provider, they only give you one public IP address. NAT is the magic that lets all your devices share that single address. And it works so well at saving addresses that it made the urgent need to switch to IPv6, well, a lot less urgent. Okay, so what do these new addresses even look like? And I get it, at first glance, they look like a crazy jumble of letters and numbers. They can seem really intimidating. But once you get the structure, they're actually surprisingly logical. So let's break down how to read the internet's new language. You can just see the difference in scale right away. IPv4, the old one, is 32 bits long, written out in 4 groups of regular old numbers. IPv6 is 4 times bigger. It's 128 bits. It's got 8 groups, and it's written in hexadecimal, which means it uses the numbers 0 through 9 and the letters A through F. So here it is, a full-blown IPv6 address. It is long, it's a bit of a mess to look at, but the good news is you almost never, ever have to write it out this way. There are 2 super simple rules that make it way easier to handle. The way you shorten this is actually pretty easy. First rule, in any group, you can just drop the zeros at the beginning. So a group like 0db8 just becomes db8. Simple. Second rule, you find the longest stretch of groups that are all zeros, and you replace that whole section with a double colon. And just like that, that giant address becomes way more readable. Okay, but that brings up a really good question. If that double colon is so great for shortening the address, why can you only use it one time? And the answer is just pure logic. A full IPv6 address must have 8 groups. That double colon is just a placeholder for the missing ones. If you used it twice, a computer would have no idea how many groups of zeros to put back in the first gap versus the second. By only using it once, there's no confusion. There's only one possible way to expand it back to its full length. All right, another huge change with IPv6 is how your device even gets an address to begin with. We're moving from a world where your device had to kind of ask a server for permission to a new world where it can pretty much figure it out all by itself. It's a process called stateless address auto-configuration, or you'll just hear people call it SLAC. Basically, a device hops on a network, it listens for the router to announce the first part of the address, and then it just generates the second half all on its own. It's a really big deal, a major shift away from needing a central boss on the network.
So you might be wondering, how does it just make up its own ID? Well, the original way, called EUI64, used the device's unique permanent hardware number, its MAC address. And the problem with that? Well, since IPv6 addresses are public, it meant your specific device could be tracked as it moved from network to network, and that's a massive privacy problem. So to fix that, they came up with something called privacy extensions, where the device uses a temporary random number instead. Much better for privacy, much harder to track.
So does this mean that central server control is totally gone? Nope, not at all. While Slack lets the device figure things out, a lot of big organizations still want that control. And for them, there's DHCP v6. It's the new version of the system we used in IPv4, where a central server is the boss, it hands out addresses and keeps track of everybody. It really just comes down to a choice. Do you want your devices to be independent, or do you want a central authority in charge? Okay, so let's circle back to that big question we started with. With all of these clear improvements, why are we still living in a world that is so dominated by the old, totally exhausted IPv4 system? And here's the answer, the single biggest roadblock. An IPv6 only device and an IPv4 only device can't talk to each other at all. It's like they're speaking completely different languages. This isn't just an upgrade you install, it's a total replacement of the foundation. And that makes moving over incredibly difficult. So to get around this, network admins have a few tricks up their sleeve. The most common one is called dual stack, which just means everything runs both languages at the same time. Another is tunneling. That's kind of like putting an IPv6 letter into an IPv4 envelope so we can travel across an old network. And then there's translation, which uses a special gateway that acts like a real-time interpreter between the two. And then you get to the hard business reality of it all. For the person signing the checks, there's just no killer feature. Switching to IPv6 doesn't make your website load any faster, and it doesn't unlock some massive cost savings. So that powerful logic of if it ain't broke, don't fix it tends to win out, especially when the old system is still chugging along just fine, thanks to that NAT workaround. So where does that leave us? What's next for the internet? Well, it's pretty clear we're not going to just flip a switch one day. For the foreseeable future, we are living in a two-protocol world. But make no mistake, the pressure to switch is building, and it's building fast. You've got the explosion of Internet of Things devices. You have the non-stop growth of mobile networks all over the world, and the insane data demands of AI. All of these things are eating up addresses like crazy. These are the trends that make moving to IPv6 not just a nice idea, but an absolute necessity. So the future, it looks like, is a hybrid one. IPv6 will take over as the new standard for the public internet. All the new addresses we need will come from there. But inside a company's private network, that familiar, functional IPv4 system is probably going to stick around for a very, very long time. And for the folks who actually run the internet day to day, what does this mean for them? Well, it means their jobs just got a whole lot more complicated. For a long time to come, system administrators are going to need to be fluent in both protocols, managing this tricky balancing act every single day. And that leaves us with one last really big question to think about. A core part of IPv6's design is that every single device can get its own unique public address. So as we connect everything, our homes, our cities, our cars, is this new world of universal trackable addresses going to force us to completely tear down and rebuild our ideas about what digital privacy even means? That's a question we're all going to have to answer together.